Hello, in this video we'll fill in any blanks that we have for Class 17 handout. The first page is a review of the self-aldol condensation. Page 2, we have a problem at the bottom of page 2 where we deal with ozonolysis. Let me show you that problem here. This is problem 1. It was page 2 of the Class 17 handout. We have this ketone. We have this alkene. And we have ozone. In organic chemistry 1, the second reaction in ozonolysis was dimethyl sulfide, or some textbooks use zinc water. We never went over the mechanism for this. We don't need to know the mechanism for the dimethyl sulfide step. But then we have base in the third step. And we are in the module where we learned about enolates. And so let's see what we get after the first two reactions, and then maybe that will give us a clue what the third reaction is doing. And so this was a multiple choice. I'm not going to draw them out. Choose the correct product, A, B, C, or D. Okay. So on a scratch sheet of paper, I'm not going to go through the mechanism. I'll go through my thinking though. We have ozonolysis, and we know that ozonolysis, we have two dots of the alkene. What happens is we split the alkene and we add carbonyl groups. How do I want to fix this? Okay, that sort of worked. So here's your dots. And it doesn't have to look pretty, it just has to have the right connections. And we have this. Maybe I should have drawn this bigger, but now we have a base. And we have a ketone. We have a diketone, but I'll call it a diketone. And we have base, NaOH. That is the classic ingredients for an aldol, and possibly an aldol condensation. And so we have a couple alphas. Thank goodness it's symmetrical. Symmetrical meaning that if you have a mirror plane, the two halves mirror each other. And we have alpha 1 and we have alpha 2. We have the same alphas, by the way, down here, but since it's symmetrical, we would get the same products. So we just have to evaluate what happens with alpha 1 and alpha 2. Remember with the aldol condensation, your enolate attacks a carbonyl that was not turned into enolate. And so whether it's A1 or A2, we're going to attack this carbon here. And so when we attack this carbon, with A1, we get a 2 rings. We have a 1, 2, 3, 4, 5-membered ring, on the left. And we have a 1, 2, 3, 4, 5, 6-membered ring on the right. If I use A2, I'm not going to draw it all, but if I use alpha 2 and connect here, you see I get a 4-carbon ring. That's too small. The angles won't allow these two atoms to be close together, but a 5-membered and 6-membered ring, those atoms do get close enough to each other to react. So that's all about, the bond angles being either too acute, like in a 4-membered ring, or too obtuse in a 7-membered ring, which doesn't allow the two end atoms to come close to each other. Okay, and so when we draw the product, let me draw it a little bit bigger. Okay, your attacker stays as is, right? It doesn't change. But let me draw it in such a way that we don't shift a lot of things. So here's your dot that got attacked, and it attacked right here. okay? Because this was your alpha. And, when it attacked, that O, don't draw this, that O became an OH. And we make the condensation right here as well, between the alpha and the beta. So let's get rid of this OH. And would I accept this as an answer if you just go ahead and draw a super long double bond? Sure. But remember, we had multiple choice. So you have to match this with what you see in the multiple choice. Oh boy. I gotta fix this. When I was looking at this ring, that looks like 7 carbons because I neglected to remember that it was only a 5 carbon ring on the right. Nuts. So let me erase this. And let's draw a bond directly to that. Okay. When we redraw, we have, what do we have here? We have a ring on the left, 1, 2, 3, 4, 5, and a ring on the right, 1, 2, 3, 4, 5, 6. Okay, and so those 2 rings share the double bond. So we have a 5 carbon ring on the left. It shared a double bond. A 6 carbon ring on the right. And the carbonyl right there. Your alpha is here. This is beta. I know this is an aldol condensation because we created again, it's good if you can memorize the classes of molecules. This is an alpha beta unsaturated. In this case, a ketone. Okay, hopefully this is one of your choices, A, B, C, or D. It looks like it is choice... Oh, interesting. It is choice B. I know that because the 6-membered ring is the one with the carbonyl. Right. Okay. Next page, 3. Okay, good. I asked for the products of a mixture of 2 carbonyls under basic conditions. So this is problem 2 on page 3 of class 17. We have these 2, and I asked you to draw what are the possible products when we mix these 2 carbonyls in base. The issue is that A could be the enolate and attacks B. A could be the enolate and attacks one of itself. So we have an AA product. And then B also has an alpha carbon with hydrogen. So both are enolizable. Okay. And again, I'm not going to draw the mechanism. But when we have A, attack A, let me just finish this part. Okay, when A attacks A, okay, let's draw A as is because I keep saying the attacker looks exactly the same as it does in the beginning. It attacked the dot of B, attacked A again, sorry. So when it attacks A again, on that dot, you have 2 more carbons. Okay. And so if you want, this is A, and this is A as well. Okay. I mean, that's the starter material, A. A attacks B. Okay, so A looks the same on the left. The attacker. When it attacks B, you notice that B only has 1 methyl group, so that's it. And that's A and B. We did this in class, the first 2. The last 2 I asked you to do at home where B is the attacker. Let me just double check my work. Okay, so when B attacks B, These are the products that I don't have. Okay, B is this. Okay, good. It attacks another B. So on the dot, you have a methyl, and your double bonds there. All right, it's 2 carbons plus 2 carbons. And then if we attack A, we have same attacker. Now A has 2 more carbons off of the dot. B, and the cut again is here. And here, B attacks A. Those are your 4 products in this messy cross aldol, because both carbonyl groups are enolizable. And therefore, on the bottom of page 3, I talked about a cross aldol where we don't get such a mess, because one of the carbonyls is unenolizable. Okay. Is there anything else on class 17? At the top of page 4, we have the Erlenmeyer, not the Erlenmeyer, but the separatory funnel to show that to make this work, make a cross aldol work well, you want the base in the round bottom flask with the molecule that cannot be an enolate. So no reactions taking place in the round bottom flask. And you want to drip in the molecule that can be an enolate, because you want that enolate, once it's made, to be surrounded by its partner. Not a bunch of itself, but a bunch of its partner. So if you look at your page 4, I have B, which can become an enolate, sit in the separatory funnel without the base. And then I drip some of that, a little bit, into a basic solution. And then once that B turns into an enolate, it is surrounded by A. A lot of A, because A was in the round bottom flask. At the bottom, page 4, again, the idea about the kinetic and thermodynamic enolate. And this one I went over in class kind of carefully, because this is coming from class 16. It does look like problem 5 on page 5 I left blank. So let me do that. This is page 5 of class 17. Okay. And this is number 5. Okay, that's why. I have this. Looks like just a ketone, but it's not symmetrical. We have 1 alpha carbon here that's more crowded than this alpha carbon that is less crowded. And it looks like we use LDA. When you use LDA, especially at low temperatures, you are aiming for the kinetic enolate, the one that's made faster. How come my 8s don't look good? Okay, so here I'll put a little note here. You want the kinetic. You run it at low temperatures, so when you make the kinetic, you don't have enough heat to go backwards to try again to make the more stable enolate, the thermodynamic. So it's kind of like a trap. You make it fast, and you're trapped in that enolate. There's not enough heat to go backwards to get over the hill going backwards to try to redo this again. So you're stuck in the product that's made faster. Or in this case, the enolate that's made faster. And then we're going to use that enolate to attack acetone. And we have a little bit of water in case we need any protons to protonate anything. Okay, and so after step 1, heck, maybe I could do the mechanism. No, I won't do the mechanism. But, okay, what is the kinetic enolate? The kinetic enolate is the one that's made faster. And so you're going to target the less crowded alpha carbon. I will use LDA only on the exam when I want to choose the kinetic enolate over the thermodynamic less crowded alpha carbon. Okay, and so when we have LDA, it's an acid-base reaction, right? And we actually don't have reversibility because we get 100% of the enolate. We get some reversibility, but in practice, it's essentially 100%. And let me do it this way. Let's draw the C enolate, okay? So that's what I mean by deprotonate, right? The alpha that's less crowded, alpha 2. But again, I prefer the O enolate. So if you draw the C enolate, that's fine because it kind of emphasizes, oh, we did deprotonate the less crowded alpha. But the O enolate, again, is this. It's actually the less stable enolate because the double bond is less substituted than if you had formed the enolate on the left. So it's a faster enolate, but it's the less stable enolate. Okay? Doesn't matter that it's less stable. We are trapped in this kinetic enolate, and we're going to use acetone as the attackee. And so this is just a plain cross-aldol condensation now. Okay, it's just that we set up the enolate in a separate reaction, and we get it to be 100% of the enolate. We introduce a new carbonyl, okay, and so I'm not going to draw the full mechanism, but etc. We have this product here. I'll swing this down. Again, this was alpha 2. And we are able to make the condensation product. Here's the dot. Here's the dot. And we have this product here. Final product. Okay. I'm also going to try to avoid actually, I could ask you if I use NaOH, what enolate do I get? But in practice, I wouldn't use NaOH on an asymmetrical ketone because then you'll start doing the aldol condensation on itself. The advantage of LDA is that you get to make the enolate first, and then you could introduce any carbonyl you want. Okay, it's just that the enolate you're going to make will always be the kinetic. Okay. At the bottom of page 5, I have the reaction coordinate diagram, and that is complete. That's it for Class 17 handout. Okay? On the next video, there is a couple things in Class 18 that I left blank. That's on the next video.